In chapter 5, we get out of differences and we move into what is often seen in statistics and in quantitative research, and that's associations. Associations and relationships. And we measure those associations and relationships using correlation coefficients. Now, you've heard of the correlation coefficient already. As a matter of fact, you saw this back in chapter 6 when we did validity. We measured the strength of, or the validity strength of an instrument by using correlation coefficients. And so you know the values already. They're going to exist between 0 and 1. We're also going to find out that you can have negative correlations or negative relationships, and so those values can fall between 0 and -1. So it's different. We will talk about statistical significance because associations can be statistically significant or not. And so that's what we're going to do in chapter 5. Our learning goals, again, are going to be beginning with, what is the meaningfulness of these associations? Do correlations provide meaningful information? And they do, for the most part. A lot of times it depends upon what we call the strength of the correlation. So I want you to be able to identify and understand what a correlation coefficient is. You're going to compute them. They're incredibly easy to do. We're not going to do any by hand because when you see the formula coming up, you'll thank me. So it's not a fun one. We're going to explore two different types of correlations. Mostly it's going to be the Pearson product moment correlation coefficient, but there's other ones. There's Spearman and other ones I'm going to show you as well. And we're going to understand the limitations of the explanatory power of correlation coefficients. We're going to take a look at something called the coefficient of determination, which is something that it just sounds nerdy right away, and it kind of is. And so that one's actually really, really hard to explain. I had to rack my brains for a long time to come up with an example that hopefully can shed some light on explaining relationships. That's kind of the hard part. Just a wee bit of background here. I mean, a lot of what we do in research has to do with associations and relationships. You will see correlation coefficients an awful lot. You will see things related to correlation coefficients in regression analysis, as a matter of fact. We'll talk about partial explanations, and we see that in regression relationships, and it's linked back to correlations. But we can understand that, and you probably already know this, that the world is an indivisible whole. Things and people exist in relationships, and sometimes those relationships can be complex, sometimes they can be strong, sometimes they can be weak. And that kind of begs the question, can you actually measure a relationship? Depends upon the measure that one uses. Now, people love to use the term correlation. I hear it all the time. I hear it from students, you hear it on TV, but what does it really mean? What does it really mean to correlate to something? We'll use a different term. We'll use the term covary because that's probably more in line with a statistical explanation. So we're going to get into what does it really mean? What do correlations mean in the context of research? And we'll get into the question, can we actually measure a relationship? So some of the examples we may encounter might be, and we're gonna work with simply two variables, which is quite nice. And we'll call those X and Y variables. You'll see those coming up. And we want to see how how X and Y relate to one another. So here's some examples that we might be interested in. I might be interested in one's level of education and that person's household income, as an example. We might be interested in the relationship between the amount of aerobic exercise I do and one's percent body fat. We might be interested in the association between the level of medication that one has and the presenting symptomology. And so we see that with some of these things, if one of the variables goes up, the other one might also go up. In some cases, one variable might go up and the other variable might go down. And so this is what we talk about when we talk about relationships. How does one variable, I like to call it, dance with the other variable? And we get to that in a little bit later on when we talk about covariance. The symbol that we use to measure associations, some of them, the major one you're going to see is a small case r, and that's a correlation coefficient, and it's going to present what we call a numerical value for these relationships. And I'd mentioned earlier, the values will fall between either a 0 and a 1, or a 0 and a -1, depending upon the so-called dance, as I call it, of the variables together. So when you see in the literature something that says, like I have here on this slide, r equals 0.72, p less than 0.05, that tells you something about well, number one, you recognize it as a statistically significant association, but that r value there, 0.72, will tell you something about the direction of the relationship and also the strength of the relationship. For the most part, correlations are fairly easy to understand on the surface, but sometimes people get tripped up when they assume that correlation implies causation. Correlation may show something that is causal, but causal explanations are really hard to show, believe it or not. And so when we talk about a correlation, we can't necessarily assume that one variable causes the change in the other. It might be the case. What we're describing really is the association between the relationship, right? So we have to get out of our heads, and you probably already know this, you've probably heard this, correlation does not imply causation. And that's an important thing. We have to be careful how we express things in terms of our research conclusions. We need to leave the term causation out of it to be on the safe side. We can talk about relationships and associations between variables, and we might be able to do some aspect of explanation, what we think is going on, but we have to be very careful before we use the word causation. And this is an example of what I mean. So, for example, more people die in hospitals than anywhere else. Does this mean that hospitals cause death? Right? For me, hospitals are places of life and the return to life in some instances. And so we can have these relationships that exist, but there might be other factors, either solo or in combination, that might contribute to the actual cause of death. In one of the earlier slides, I had mentioned the x and y variables. And one of the easier ways to see if there's a relationship or not between variables is to look at what is called, we can actually do these in SPSS, create what's called a scatter plot graph. And a scatter plot graph shows where two variables exist at the same time. So I'll measure something on the x or the horizontal axis, and that same variable I can measure on the y-axis at the same time, and that gives me a singular point. And so these scatter plot graphs have a series of data points on them. You'll see on the next couple of slides coming up. So I think this is an example right out of Salkind. And so here we have, if I'm measuring two things in a person, or two different variables, I can actually combine them on a singular graph. So on the x-axis here, we've got these values 1 through 10. I'm not sure what this measure might be. And on y, we have the measure up here as well. I'm not sure. This might be, I just can't think of a value for 1 to 10 that I'm measuring anyway. But what we see here with scatter plot graphs is you begin to see some patterns that emerge. Just like we saw with the normal curve, we begin to see what we saw with histograms is we began to see patterns that emerged. And so patterns emerge here as well when we look at the relationships between the x variable and the y variable. It seems that as, in this case here, as x increases, so does y. Right? So on the bottom here, x goes to a value of 3, and y also goes to a value of 3. this value over here, x goes to 8. In this case here, y also increases, not quite as high as 8, but up to 6. And so we see these patterns that begin to emerge when we see the data points plotted as a scatter plot. And so the symbol that we use, this R value, really is telling us a bit about the interaction between the X and Y variables, right? They're two variables that we measure, and they're supposed to have some kind of an association together with one another. So when you see an R value expressed, really what you are seeing is they're saying, the symbol is saying to you, this is an expression of the relationship between the X and Y variables, whatever those things you are measuring together, right? So it might be the amount of cheese that you're eating and the level of pain in your stomach ache, for example. And so, the question is, if X moves in one direction, what's going to happen to Y? Will it move in the same direction, or will it move in the opposite direction? We'll get into that a little bit later on when we talk about direct and indirect relationships between these X and Y variables. So we can begin to describe these patterns now. So this scatter plot here shows what is called a positive or a direct association. And what that means in a direct association means this: if the X variable increases, that means there's going to be a concomitant increase in Y, which means that Y also increases. Now, Y may not increase to the same extent as X, or it may actually increase greater than the extent of X. And so we start getting into these scatter plots that are, less than perfect. I mean, a perfect relationship would be this: if X goes up 1, so does Y. If X goes up 2, Y goes up 2. And so you would have a straight line. A straight line would indicate a perfect relationship between X and Y variables. But they're rarely perfect, right? In this case here, there seems to be a pattern where it seems as X increases, so does Y, but it's not a perfect pattern. Now, if we can have a positive relationship between two variables, we can also have what we call a negative relationship between two variables. And so we call this an indirect relationship, right? So in this case here, as X increases, what happens to the value of Y? Well, the value of Y decreases. And so we see this. The scatter plot here is a bit of an odd mirror image of the previous one. When X goes up, Y actually goes down. And so this happens with some relationships. I gave an earlier example of aerobic fitness and percent body fat. When one engages in aerobic exercise, what happens is your aerobic capacity goes up, but the more aerobic exercise you gain you do, the more calories you burn, and fat is often used as a primary fuel in moderate aerobic activity, and so over time your percent body fat goes down because you're burning fat. So my aerobic capacity goes up, at the same time my percent body fat goes down. And so again, it's not going to be a perfect relationship, because rarely in the real world do you have perfect relationships. The only perfect relationships you ever see are in textbooks, by the way. They just try and make it easy for students. It's not a bad idea. In the real world, the data is always messy. It never looks like it is in a textbook. Trust me on that. Anyway, so we can also have negative or these indirect relationships. Now, the underlying principle with correlation coefficients is this concept called covariance. And so we say that the two variables covary together. And we know what variance is, right? We know we're talking about the distance that they are apart. In this way here, we can describe that as, how these variables change distance with one another might be one way to describe it. But that's even a little bit odd. It's a little bit odd. Textbooks sometimes don't do a very good job of explaining covariance, and I struggle with explaining it too, to be quite honest. So one of the better ones I've come across is covariance might be more intuitively explained as a measure of how much two variables change together. Now understand that sometimes two variables don't change at all. Right? If the variables don't change at all, sometimes that means there's no association between the variables. This is simply a moot point. We can move on. There really is nothing to see here. Sometimes variables change a little bit with one another. Sometimes they change a lot with one another. And so we talk about this aspect of covariance. I liken it to this instead, and this makes a bit more sense to me when I'm trying to conceptualize statistics. I think about covariance as how two variables dance together, right? And I have that on the next slide. Yeah, I like my definition better. How do two variables dance together? I suck at dancing. From the waist up, I've got great coordination. From the waist down, I don't. I could never play soccer, still can't. I think it's why I picked up bicycle racing, because you strap your feet in and your legs move in one plane of motion. Pretty easy for me. But if you've ever gone and watched people dance, and there's different types of dances, right? Sometimes you're going to get two individuals who are dancing, right? And I talk about the separation here between X and Y, and really they're doing their own thing. X kind of wants to dance with Y, but Y is sort of he's doing his own thing. And so they're not dancing together very well, right? They're kind of dancing independent of one another. And so we would say that when two variables are doing their own thing, X kind of wants to do this and Y kind of does whatever Y wants to do, and not very consistently, then we say that those two variables don't covary very well, and we would actually see a very small R value, an R value closer to 0. Comparatively speaking, we've got something a bit more elegant, refined, is ballroom dancing. So if ballroom dancing, usually one variable moves and the other variable follows, and you have this wonderful fluid pattern of motion between two dancers. And so when X moves, Y is going to move with it, and depending upon the pattern. In this case here, if X moves in one direction, Y will probably move in the same direction. So maybe for dancing, that might be best described as a direct relationship here. So again, you've got some aspect of leading and some aspect of following. The more X moves, the more Y is also going to follow. And so we would say that both X and Y are strongly covarying with one another. And in that case there, we would see a larger R value between the two relationships, maybe an R value closer to 0.8, for example. Let's move from dancing back into some of the symbology with statistics. And so X and Y are the two variables that are dancing together. And when I see the value of X move largely in one direction, and I see that the value of Y also moves in the same direction largely, we say that they are moving together in similar patterns. They're moving together largely, but also in the same pattern, in the same direction. Same thing if they were small. If X gets smaller, Y moves in the same direction. It also becomes smaller. We say that they are moving together in similar patterns, which means that they are covarying. Covariance falls apart when X might move largely and Y may not do anything, for example, or it may move even slightly in the opposite direction. The same thing if I've got X that begins to get smaller and Y doesn't do anything. That's when covariance actually ceases. And when covariance ceases, what happens is the correlation coefficient becomes rather small. I've been alluding to this all along, this particular slide, and this particular slide has to do with how we measure R values. And again, depending upon the direction of the relationship, if it's an indirect relationship, the R value is going to fluctuate between 0 and negative 1.0. Okay, and so the closer you are to negative 1.0, that tells me how strong the negative association is, or how strong the indirect relationship is between those two variables. On the flip side, on the positive end of things, or the direct relationship, the R value is going to vary between 0 and plus 1.0. Okay, so again, the stronger the positive relationship, the closer that R value is going to be to the value of 1. Just a quick point here, again, just differentiating between positive correlations and negative correlations. If I have a positive correlation, the R value itself is positive, and this means both variables are moving in the same direction. When one increases, the other variable also increases. A negative correlation is when an R value is negative. We call this an indirect correlation, and this is when X increases, Y is going to decrease. While there are many different types of correlation coefficients, and you'll see some more at the end of this presentation, the most commonly used correlation coefficient is what we call the Pearson product moment correlation coefficient. That is definitely a mouthful. We often call it the Pearson correlation coefficient. Now, the type of variable that works or that you have to use with the Pearson coefficient is a continuous variable. That is to say, it's got to be either interval or ratio. If you are using a Likert type scale or an ordinal variable, you can use a Spearman correlation coefficient. So you'll see Pearson and you will see Spearman the most in terms of the types of correlation coefficients that you will see in the literature. Now, I mentioned before that the strength of the relationship depends upon the absolute size of the R value. Okay, so remember, if I see something like an R value that has a negative in front of it, that doesn't mean that this is a weak correlation. That the negative simply tells me the direction or the type of correlation coefficient. In that case, it would be an indirect or a negative correlation coefficient. As X increases, Y decreases. But we have here again associating the scatter plots with the size of the R values, and so we begin to see that a scatter plot like this looks like a bit of a shotgun blast here. We might have an R value very close to 0. So there's no relationship between the X and the Y variables. They're doing their own thing, right? X is dancing over here, Y is doing their dance. They're kind of on the dance floor together, but they're not really dancing together. They're dancing, just not together, okay? The correlation of minus 0.3, you might begin to see a bit of a pattern begin to emerge, but it's still kind of hard to see. So this would be a fairly weak correlation. Once you get up to a correlation value of 0.7, you begin to see some of these patterns that emerge, and although they're not perfect necessarily, you begin to see some sort of, in this case here, it's a negative pattern that occurs. These are beautiful correlations here, the one on the lower right hand corner. I mean, this is a correlation pattern of negative 0.99. I mean, rarely are you going to see this. I've seen some 0.98s before in some of the physiological literature. It's sometimes some things are just a lot, the values that are easier to measure, more directly measurable, and the associations are strong. You can see, how these data points almost line up in a straight line. Still not perfect. You're never going to find a perfect relationship because of error, but you can get some other even this 0.9 relationship here on the side, this positive relationship here. You really begin to see some of the patterns that emerge. So this slide here shows the R value strength along with the visual representation of the patterns. We've got the negative associations or the negative or the indirect relationships on the right-hand side. On the left-hand side, we have the positive or the direct associations. This is I should have warned you about this slide coming up in the previous slide, but this is the math in behind computing a simple correlation. And so you're not going to do one. You're welcome. But it's actually not too bad. We see a lot of the sigma signs and X's and Y's, and we're squaring things and creating fractions. But this is what it is. So in the Ghost in the Machine and SPSS, when it's running a Pearson product moment correlation for you, this is the formula that it's running. So this is a general rule of thumb. I mean, I think I pulled this from. Did I pull this from Salkin? I might have pulled it from Salkin. Here we go. So anyway, here is on the left-hand side, we have this range of values for the size of the correlation or the R value. We go from 0.8 to 1, then a little bit less, 0.6 to 0.8, et cetera, all the way down. And so we say that if we've got a correlation value between 0.8 and 1.0, it's a very strong relationship. And onwards and downwards, right? You get down to 0.2, it's weak or no relationship. Now, I have to pause here for a second and explain something. This is, again, this is a rule of thumb. In some of the more lab-related sciences, where you can control an awful lot of factors, right? This is where some of these values come into play. You know, we like to see values anywhere from 0.7 to 1.0, or close to 1.0 in a laboratory controlled setting. We would then call those fairly strong. In some of the sociological sciences, where you're working with very large data sets with an awful lot of variability, that is to say, there's a lack of control over a lot of things, you can have correlations in the 0.2 to 0.4 range that technically are weak, but because the sample size is so large, these correlations can be statistically significant, and they become a big deal. Some social scientists get very excited if they get an R value of 0.3 that's statistically significant. They get very excited about that. The laboratory scientists would go, "Are you kidding me? That's nothing. We need the 0.8s." Well, you're not going to have a lot of 0.8s in large data sets with an awful lot of variability, right? It just doesn't happen. And so while we label these correlations or qualify them, weak to very strong as an example, part of it depends upon the context, right? Is it social science, psychological type studies where there's a lack of control of some of the factors in the research, lots of variance? Or are these studies where they're highly controlled? Highly controlled, we control everything, and so there, a small correlation, although it's significant, may not have the same amount of meaningfulness as something that has a correlation value that is very large. Just like with t-tests and analysis of variance, we still run null hypotheses with correlations. And so the null hypothesis for correlations is that R is going to be equal to 0, right? That is to say there's no relationship. We think there's going to be a relationship. That's our research hypothesis. And when we say there's no relationship, we know that the R value is going to be equal to 0. Those variables are not dancing with each other whatsoever. So one of the first things that we do when we interpret a correlation statistic, the first thing that we do before we take a look at the size of it, is we have to see whether or not it is statistically significant. Even if that R value is large, it doesn't matter. The first thing that you need to do before you discuss anything about the strength of the relationship between two variables is to see whether or not that relationship is statistically significant. That is to say, if you set your level of significance at 0.05, that means your p-value associated with the R value, and SPSS will give you this, has got to be below 0.05. If it's not, if it's above 0.06, you don't talk about the R value. Why? Because it's not significant. You don't. And what if it's 0.7 or 0.8? Isn't that strong? Doesn't matter. It's not significant. If it's not significant, then it means it's highly likely that that correlation happened by chance, and so you don't talk about it. You don't discuss anything about it. You say there's no association between these two variables. Full stop, and then you move on. And this is why sometimes you can have small R values that are statistically significant, and you can talk about those. Right? They're harder to talk about because the strength isn't there, but it's statistically significant. So you have to kind of unpack the meaningfulness of the association, and that's the hard part for the researcher. It's kind of easier to talk about a strong correlation value of 0.8 and it's statistically significant. You can talk about the meaningfulness of it. But the smaller ones can be more challenging, right? So just because the correlation value is small doesn't mean that it may not hold some level of importance, and it might in very, very large sample sizes, right? That it could do that. Let's run an example of a correlation here. So if you've ever been in an examination, you ever notice sometimes, like maybe 10 minutes in, someone is done, they hand in their exam and they're gone? Or are you one of those people who stays till the very end and there's that one person with 2 minutes to go, they're still writing away and you're handing in your exam? So you ever wonder whether these people did either really well or really poorly? Sometimes people hand in their exams early and they might have done actually really, really well. And sometimes people use all the time to write their exam, and they might not have done very well. What could we hypothesize here? So we could hypothesize that people who take the longest on exams are the most careful, therefore they score the highest. So if you were to run a correlation between time taking to write an exam and scores on an exam, you would see something that looks like this in terms of a scatter plot. So this would be our expectation, that we would have a positive correlation between time on the exam and grade on the exam. And again, the positive correlation is as time increases, so does the grade on the exam. Or we could hypothesize that the longer it takes for a person to write an exam, the longer test taking is associated with poor scores, maybe because they didn't study or prepare enough. And so what we would expect them in terms of our output, our correlation, would be this, to be the opposite. This would be an indirect, what we call a negative correlation. As time increases, the grades actually go down, and so you would see a scatter plot that looks something like this. And so here's some hypothetical data. Here we have our student, right? We've hidden their names for confidentiality issues. We've given them simply a letter. Here's their grade on their exam, and there's the time it took in minutes on the exam. Here's the mean, here's the range of the scores, and the standard deviation for both the grades and for the time on the exam. So now what we want to do is we want to run a correlation analysis on this data to see what the association or what the relationship is between the time on the exam, how long it takes me to write an exam, and one's grade. And this is the scatter plot that we get. We actually see a positive relationship. So this is what the data is telling us, that as time on the exam increases, one actually gets better grades, okay? And so this answers part of the question over here on the side. What is the direction of the relationship? So we would call this a positive relationship, right? As time on the exam increases, so do grades. When I run my correlation and I get my SPSS output, you would see something that looks like this. You get your descriptive information here. We saw that on the previous slide. And then we would have this information here. Here's what we call a Pearson correlation coefficient. And I mentioned before, this is the one that runs with continuous variables. And so what we see here on the output is we see a correlation. Like this is an R value. This is how we express the correlation. Again, we've got a value of 0.642. Those little asterisks there tell me if it's significant or not, and lo and behold, it is. The correlation is significant at the 0.01 level, right? So this is what it means. As a matter of fact, SPSS actually gives us the direct p-value of 0.002. So this is much less than 0.05. And so we would say that there is a statistically significant correlation between time it takes to write an exam and the grade that one gets on the exam. And this would be our conclusion here. Pretty straightforward stuff. Like correlations are probably the most simple, not only to understand, at least I think, but also they're fairly easy to write up. Usually they're one sentences, right? We ran a Pearson correlation on these two variables. Here is what we found. We had an R value of 0.642, p less than 0.05. Therefore, we can conclude that the longer the time taken to write an exam, the better the score on that exam. This is the wonderful thing about associations. They're fairly simple to write up. We don't have to worry about an interaction effect like we did with two-way analysis of variance. We're not looking at critical values of t and calculated values of t. We look at one simple output, the R value, and its associated p value. Now, after I've said all this and have gotten into the simplicity of it, I'm going to take us a little bit further and we get into something a little bit more complicated called the coefficient of determination. So the coefficient of determination is something that we call the R squared. And you've guessed it, to calculate the coefficient of determination, you simply take the R value that we have from a correlation and we simply square it. That's all we do. But the coefficient of determination indicates the true strength of the association. I know that I showed you a table before of different R values and their associated qualitative strengths, weak to strong. But the coefficient of determination is the one that we like to take a look at a bit more closely. And there's another reason why I'm introducing this to you. It's not to frustrate you, but we will see the r squared component, or the r squared value. We'll see that when we get into chapter 16, linear regression. Okay, so that's going to come up again. So I want to show this to you now. If you get lost in this part of the presentation, I've put together a handout on the very same thing. It's in written script form in an MS Word document, so you can also take a read of that as well. The definition of the coefficient of determination is a little bit, I'm not sure it's that helpful, actually. I think examples sometimes give us a better sense of what is going on. But here's the definition. It's the amount of variance in one measure that is explained by the other measure. Say we're trying to say something about one variable can explain the change in the other. This is where we get into the explanation side of things. Before I talked about a correlation coefficient as a dance together, if we're talking about, a shared variance, so to speak, or covariance, not shared variance, but covariance. And now we get into shared variance. And so, for example, if I've got an R value fairly strong of 0.91 between height and foot length scores, the R squared, or the coefficient of determination, is going to be 0.83. And so what this means is 83% of the variability in foot length scores is due to or can be explained by the different height scores. And again, that's a bit of an odd thing to say. So another way of looking at it might be this. We have 83% of the information necessary to make an accurate prediction. That's what we're talking about here. So there's more of a usefulness of it. But I'm going to try and explain it a little bit further for you. Sometimes visuals help. And this one here is we have the in two different columns here. We've got the correlation and the coefficient of determination, and then we have the variable x and the variable y, because these are the things that we are associating with one another. And so on the far right here, we have a visual representation of what is going on. But if I've got a correlation of 0, right, there's no relationship between x and y. They're not connected in any way, shape, or form. The coefficient of determination will also be 0. There's nothing that we can say about x that is going to predict or explain anything about y. Okay. If I've got a correlation, this is a moderate correlation of 0.5. The R squared value, actually, if you take a look at it, the coefficient of determination is always much smaller. Anytime you square decimals, you're going to get a smaller value. And so what we say here is that the R squared, or the coefficient of determination, is 0.25. Or there's something about the x that explains 25% of the change in y. So it doesn't explain much. It's explained some, but not all the change in y. Okay, so the last one here, notice that the correlations are getting stronger. The last correlation here is 0.9. Well, when I square that, that gives us 0.81 or 81%. So the change in x will explain about 81% of the change in y. There's something about there's something that those two variables share. Okay, this is what I mean by shared variance. There's something that those two variables share, that if I have a value of x, I can predict the 81% of the change in y. Now, the hard part is, what exactly do these two variables share? This is one of the weirdest things, and one of the things in statistics that is not explained very well. The term is thrown out there, R squared shared variance. We're expected to know what that means. But it's hard. It's hard to unpack that. So I've got an example coming up that might explain. Hang with me and see if this next example works for you. And the example that I want to show you is a classic one. It's a height and weight example. So what we see generally is people who are taller are heavier than people who are shorter. In general, we know that's not a perfect relationship, right? So let's just say that we ran a correlation of a sample of people and found that we actually had an R value of 0.68, and it was statistically significant between height and weight. So there's an association there that is moderately strong. Okay, the R squared value would be 0.46. Or that height and weight share about 46% of the variance. And again, we get to the question then, but what is it exactly that they share? And so we have a couple of explanatory options here. So for example, can an increase in height explain an increase in weight? Or conversely, can an increase in weight explain an increase in height? Well, the second one is probably less likely than the first. So let's take a look at the top one as a possible explanatory option for this concept of shared variance. You know, I've racked my brains. This is again the fourth year I've taught this course, and for the longest time I had to rack my brain for an example. I finally pulled out one from my biology years from years ago, and I remember that when we grow, for example, right, in terms of height, part of our height is due to what we call these things that are called epiphyseal growth plates, right, and they're in the ends of the long bones. And in it, we have cartilage, and these cartilage cells cells proliferate. They grow, and as they grow, what we see is the bones actually get longer until such time as these growth plates solidify. They actually fuse together, and this is why you stop growing. And so, so we do have this aspect related to growth in height due to the elongation of the long bones. But we also know that as we grow, we actually accumulate mass via cellular division. So by virtue of biology and genetic expression, these cells divide at the same time. And that's what's actually forcing the growth. But we also retain these cells, right, as well. They don't go anywhere. We retain them. And of course, part of this is due to, you know, I have to keep eating in order to do this. But we have this connection here now with respect to height, right, and also cellular proliferation. Again, just a little bit more information here. Again, these growth plates, again, contain cells that proliferate, right? They proliferate cartilage. Now, eventually, these areas are replaced by bone, by calcium phosphate. And eventually, those growth plates fuse together and you stop growing. Okay, and so at some point in time we stop, but during that time we've had cellular proliferation and we've also had an increase in height. And so what can we take away from this? Where am I going with this? And hopefully I haven't wasted, you know, 7 or 8 minutes of your life. So we know that this increase in cellular mass by virtue of cartilaginous proliferation, that's really hard to say, causes an increase in height. Okay. But the increase in mass that we retain also causes an increase in weight. That is to say, the more cells that divide and we retain, that actually adds up to more weight. And so this is what I mean in terms of what exactly are height and weight sharing, right? That explains part of that variance, right? The shared variance. What exactly are these two things that are sharing, height and weight, that account for this relationship? And what it is, it's an increase in cellular mass. And again, here's our answer a little bit more directly. Back to the original question, what is it that both height and weight share that would explain an increase in one that would also explain an increase in the other? We're trying to find what exactly are they overlapping with. And so the answer here is mass proliferation. But mass proliferation is in a particular direction, up, right, which we call height. And so height does partially explain weight. That's that aspect of shared variance. But it doesn't explain all of weight. As a matter of fact, in my example here, and I don't know if this is the case or not, I simply use this as an example. Height only explains about 46% of the weight in this particular example. So we still have a remaining 54% of variance that is unexplained. So what is it about increases in weight that is unexplained? Height only in my example here explains 46% of that. There's still 54% that remains unexplained. And this unexplained variance is known as, it's called the coefficient of non-determination, or even more lovely, this is a real huggy here, the coefficient of alienation. So it would be 1 minus r squared. And again, this whole concept of shared variance, I mean, we know in the real world there are often many factors that contribute to the outcome of another. right? So what else might have contributed to height and weight? Well, nutrition is probably a big factor there, okay? Nutrition probably plays a role. Gravity might play a role. All different kinds of roles that actually can explain increases in weight. So height only accounts for part of it. And this is why we spend some time with correlation first before we get into linear regression. Because when we get into chapter 16 and we get into multiple regression, we have a way to look at multiple variables that might have an influence on an outcome. So for example, we might be able to come up with a model that involves height, nutrition, and gravity that might explain a change in weight. And so that's multiple regression. But we have to cover that concept of shared variance here first before we can do that in chapter 16. I don't think that Salkind covers, well, he does cover other correlation coefficients, but not to the same degree. He pretty much just runs them by you, so you're aware of them. But there are other special correlation coefficients. One of them is called the Spearman correlation coefficient, and this one is used sometimes. You'll see it in the literature. And we use this one specifically with ordinal variables. Okay, so use the Spearman, it's called Spearman's rho, is what it's called, and you'll use that with ordinal variables. But the next slide gives a table of other types of correlation coefficients. We've been working mostly with the Pearson correlation coefficient. I do that because Salkind mostly works with it, and that's the one you're going to see most of. You might see Spearman correlation coefficient. And remember that the Pearson correlation coefficient uses continuous variables only. Spearman uses ordinal variables. So it's ordinal and ordinal, you're comparing a relationship. But what if I want to compare something like a nominal variable to a continuous variable, or an ordinal variable to a continuous variable? These types of things. This table is from Salkind, and so we have examples here of different types of correlations and their names. Right, so if the variable x is nominal, this say, and the variable y is also nominal, so nominal and nominal, I can use something called a phi coefficient. Okay, if I want to do a correlation between a nominal variable and an ordinal variable, I can use something called a rank biserial coefficient. If I want to use nominal variable on an interval variable, I can use something called a point biserial. I just want you to be aware that there are other types of correlation coefficients, and we're not restricted specifically to continuous variables and ordinal variables like we see with the Pearson and the Spearman's correlation coefficient respectively. And just a quick summary slide here. You'll get a chance to, with some practice questions with respect to correlation coefficient. Your practice example, you'll run some data. Again, this doesn't take long to do. I've got some videos for you from YouTube for you to go through. And you'll get some practice not only running and we'll keep it to the Pearson correlation coefficient. That'll be enough for us for now. You can run one of those and also do an interpretation of the data.